So my name is Shubham, and today I will be talking about the two-stage approach for single pulse post-processing. And I am presenting this work on behalf of the SKPSS team. So I will start by introducing the post-processing parameter space. So a fast transient event is described by three parameters in addition to its sky location. So these three parameters are DM, time of arrival, and width of the pulse. And when a fast transient event at a given time, DM, and width goes through a single pulse search, we end up finding a lot of duplicate detections. So number of detections can go up to 1 million in case of a very wide and very strong pulse. And a big fraction of the detected events are not even astrophysical. Most of them are RFI generated. Now to handle this thing, we have this post-processing step, which has two parts. So the first part is clustering. And in this step, we try to identify the duplicate events, duplicate detections of an event, be it RFI or astrophysical. And then in the shifting part, we try to reject the RFI clusters based on the property of the cluster itself. Now I will discuss a few clustering methods. So first in the line is the friends of friends. So this method is fast and it can handle a large number of detections. The method is based on linking and it requires a user-defined linking length.
Hey Shubham, sorry to interrupt. We think you might be using your headphones mic, which is probably unstable and is leading to some crackling noise. So is it possible for you to just use your laptop mic instead?
Is it okay now?
Yeah, this is better. Thank you.
Okay. So again, the friends of friends method is based on linking and it requires a linking length defined by the user. And this method cannot handle stray noise in the data and it also cannot handle variable density. So in the data set on the right side, we have two clusters and the stray noise in between them. So if we run friends of friends on this data set with a linking length indicated here, then we will be able to identify the two clusters, but the noise point will also be identified as a separate cluster. Now what if we select a wrong linking length? So if we select a linking length indicated here, so this length will be able to connect almost all the points in this data set and we will be left with a single cluster. And in this situation, we are losing at least one cluster here. So the second method is DB scan. So this is also reasonably fast and it can handle a large number of detections at a time. And this method is based on density and it requires two user-defined parameters, a length scale epsilon and a number n. And these two parameters are used to decide the lower limit on the density. This method can handle noise, but it cannot handle variable density. So in the data set here, we have two clusters. The upper cluster is sparse, while the lower cluster is more dense. And when we run DB scan on this with a length scale indicated here and n equals to 5, we can identify the lower cluster, but the upper cluster, which is not as dense, is identified as stray noise in the data. So here again we are losing one cluster. Now the next one is the SDB scan. So this is a modified version of DB scan and it only requires a single user-defined variable, which is the size of the smallest cluster. And this method can handle variable density, and it can also handle stray noise in the data. So here in this data set, we have 3 clusters and 2 stray noise. And when we run SDB scan on this with a size of the smallest cluster being 5, then we are able to identify the first 2 clusters, even they have different densities. But the last cluster with only 4 members has been identified as noise. This is because the smallest size of the cluster has to be 5. So this says that in this method we may sometimes lose very small clusters, but means this is the best we can do. And this also means that with this method we sometimes may lose very narrow pulse and very weak pulses. So in the case of very wide and very strong pulses, we have another problem. So the detection process itself gives a lot of independent looking structures, and when we run SDB scan on this, we get a lot of clusters for a single event. So this is not correct. We have to unify these clusters. So for this, we remember one concept where if you have a pulse of size W, then you cannot have another pulse with similar width within a radius of W. Now we go back to these small clusters and we select the brightest detection here, and then we draw a circle of radius W around it, and then any cluster within this circle will be labeled as same because they belong to the same event. So by this extra step, we reduce the number of independent cluster for a single event from 100 to a few, and you can also see that the yellow cluster here is a good approximation of the actual event. So what is the optimal approach for clustering? So I will say SDB scan followed by the additional step of clustering based on the detection width. So now we move to the shifting. So the aim of the shifting step is to reject the RFI clusters. And for this, we first need to understand the difference between an astrophysical cluster and a RFI cluster. So on the right hand side here, we have DM versus time plot and SNR versus DM plot of a astrophysical event. And in the bottom here, we have the same plots for the RFI event. And if you look closely, you can already identify a few differences in the RFI versus astrophysical events. The main difference here is that the SNR versus DM plot of the astrophysical event has a very sharp peak, while the same plot is almost flat in the case of this narrowband RFI. So our aim here is to select a few cluster features that describe these differences efficiently. And while selecting the cluster features, we have to keep in mind a few things. That we should not select a lot of features, because a lot of features will make the shifting step expensive. So we have to select a limited number of efficient features. And second thing is that we should not try complex fitting on the cluster data, because the fitting can be very expensive for very large clusters, while it is not very reliable in the case of small clusters. And the third thing is that we should also not use any feature that can introduce a bias against a subclass of the target. So like we should not use a feature like shape of the pulse itself in the classification. So once the features are selected, we can do manual thresholding on these features. So for example, if you put a lower limit on the size of the cluster, you will get rid of most of the random noise detections. And if you put a lower limit on the base DM of the cluster, you will get rid of most of the wideband RFI clusters. However, getting rid of the narrowband RFI can be slightly non-trivial. So for this, we need more complete and automated way. So for this, we try supervised machine learning methods. So first one is the decision tree. So this is a simple and interpretable method. However, the accuracy for this method is not very high. It can go up to 70 to 80%, and it can also sometimes overfit. The second method here is the random forest, which is an ensemble of randomized decision trees, and the final decision is made by the majority voting of the decision trees. So this method gives a good accuracy, which can go up to 90 to 100%, and this is also simple and flexible. The last method here is the neural network, which gives accuracy similar to the random forest, but it is slightly harder to interpret. So we decided to use random forest in our shifting for its accuracy, flexibility, and simplicity. And with our selected set of features and simulated data set, we easily achieve 96% accuracy in our shifting. So since the shifting is not the final classification, so we would not like to lose any astrophysical signal in this step. So random forest has a very flexible way of reducing the false negative rate. So you can tweak the voting step. So a regular voting will say that any cluster will be astrophysical if more than 50% of the decision tree says so. Now you can tweak this to say that a cluster can be identified as a astrophysical even if more than 40% of the tree agree. So in this way, we are reducing the chances of astrophysical signal being misclassified. So what is the optimal approach for shifting? So there is no optimal approach, but simple set of features combined with the random forest classifier do a very good job. So in the PSS Cheetah, we have implemented a few algorithms for the post-processing step here. So for the clustering, we have friends of friends, which is faster approach, and and then we also have the SDB scan followed by the additional step of clustering, and this is the more robust approach. And then for shifting, we have simple thresholding and the random forest classification. And for the best results, I will recommend SDB scan followed by the random forest shifting method. So in summary, the single pulse post-processing has two parts. So first part is clustering, where we try to identify all the duplicate detections of an event. And for us, SDB scan followed by an additional step does a very good job. And for shifting step, the shifting step tries to reject the RFI clusters, and random forest classifier combined with a simple set of features does a very good job. And also random forest classifier has a very good flexible way to reduce the false negative rate, which means that we are reducing the loss of astrophysical signal. So thanks. So this is all.
Thanks, Shubham. Questions for the speaker?
I have one doubt in the random forest. So when you apply RF, so RF classifier, you apply on each candidate or in or on cluster.
So we apply it on the features of the cluster. Like okay, so we select a few features. Like these are the features uh, uh, that we use, and we
Oh,
apply random forest on these features.
okay, okay, okay.
Yes.
And in can you go back in the width? You add the width in the HDB scan.
This one, yes.
Yes, yes. So, in the this plot, I can see that the candidates are present. Like when you group them into one cluster. So, so what exactly you are actually doing? I am not get the part correctly.
So what happens that we want one single cluster for a
Yes,
single event. But here, what we are getting a lot of cluster for a single event.
but the time of arrival are different, na? So you should form different clusters.
So this is a very wide pulse. This is a 1 second wide pulse. So you get a
Oh,
lot of independent looking small structures.
okay.
Yes.
So based on the width, you group them up.
Yes. Yes.
Okay. Oh, ठीक है. Nice. Thanks.
Thank you.
Any more questions?
One more question. When you
Yeah.
use FOF, so you on
Hmm.
use on a CPU or GPU based?
This is CPU based.
CPU. So in
Yes.
FOF, use the uh, wait, uh, DFS, right? Depth
We use
first search.
means we have our own implementation which is based on uh, R
Are
tree.
you using KD tree or any Annoy or any other system for that?
I think we are using some tree. Its name is R tree and it is available in Boost. I think
Uh,
Boost library.
okay. And okay. Thanks.
Okay, any more questions? I guess I'll ask one. So you were talking about some random forest classifier where you said that a certain number of clusters, let's say 50% classify as a source as astrophysical. So you say that it's a truly astrophysical source. So in that scenario, do you actually also like think of that parameter as, let's say, a hyperparameter and optimize it such that the false alarm rate is minimized or something?
Yes, means in this with this one can I think reduce the false negative rate to uh, an optimal value. Means these numbers are just for example here.
I see.
Uh,
Okay.
yes.
Oh, there's a question.
Where in the one in the 2 slides or 3 slides previous to this one, you have the
Yes. No.
this
Yes.
one, so you have SNR versus DM plot for RFI. So
Yes. Yes.
always RFI look very different from what you have for the astrophysical signal, or there are RFI situations where you can confuse with the astrophysical signatures.
Yes. Means so what happens with a narrowband RFI? If it is strong enough, it will be detected across all DMs because it is not getting dispersed, and it will be detected with similar SNR. And same can be said for a very wide pulse. If you have a very wide pulse, the dispersion due to the small change in DM will not be very large, and you will get similar SNR. So yes, means for very wide pulse and for a narrow band RFI, you get similar SNR versus DM plot.
And what will be the DM versus time plot in those two scenarios?
Actually, DM versus time plot look very similar. The only difference is the ratio of the extent in DM and extent in time. Uh, I think that is not quite true as well. Means things can be very similar for a wide pulse and for narrowband RFI.
Okay, thanks.
There's a question by Raghu.
I mean, it's not a question, it's comment, probably trying to defend Shubham. So in case of narrowband RFI, the RFI would start from 0 dm and then extend both the axes, just like a bow tie but cut in half. And yeah, that's the case. Yeah, but usually, I mean, some things are already mitigated by RFI algorithm. So one needs to also remember that there is such step of RFI mitigation before this happens. So I guess.
Yes, yeah. Means the final candidates still are mostly RFI and astrophysical. Means most of them are RFI. So we have to face this situation. But yeah, means there are gaps in this method.
Okay, any other final thoughts, questions, or comments? I guess we can stop there. Let's thank our speaker again.